State-space representation is used to model complex systems like free body diagrams and circuits. In this video, we will be showing you how to model a circuit with state-space representation, which is given by a first-order matrix differential equation. This is the standard form for state-space representation. Here, x represents the state variables of the system, or the total internal state of the system, u represents the inputs, and y represents the outputs. Matrices A, B, C, and D contain coefficients that linearly combine the state variables and inputs to determine the state and output. For most circuits, the matrix D is null because there is no direct feedback. Here we have a third-order parallel circuit with an inductor, a capacitor, and a resistor and inductor in series. On the left, we have basic circuit equations like Ohm's law and Kirchhoff's law. We have defined the state variables as I1, V1, and I2, written in blue. There are 3 state variables, since this is a third-order system. State variables are not unique, so we could have picked a set of 3 other variables, but for the purpose of this video, we are using these variables. Let's say we have an input current of I, and we want to find the output V2. We would want to rearrange and rewrite the circuit equations to solve for the derivative of the state variables, since the standard form is the derivative of x equals ax plus bu. For the first inductor, we can solve for di1 dt directly from the inductor equation. For the capacitor, we cannot solve for dv1 dt quite yet because IC is not one of our state variables. We first would have to put IC in terms of the input and state variables. Looking at Kirchhoff's current law, IC equals I minus I1 minus I2. We set that equal to C dv1 dt, and now we can solve for dv1 dt. For the second inductor, we also cannot solve for di2 dt directly, since V2 is not one of our state variables. However, based on Kirchhoff's voltage law, V2 equals V1 minus I2R. Now we set that equal to L di2 dt and solve for di2 dt. Finally, we want to define our output equation. To find V2, we can use the same equation from our work to determine our second inductor. V2 equals V1 minus I2R. Now that we have all of our circuit equations, we must rearrange them into differential equations. Once we have all of our equations defined, we will translate the differential equations into standard form with matrices. As we defined earlier, x contains the state variables. Since there is only one input and one output, u and y are both scalars. In order to translate the differential equations into standard form with matrices, you take all of the coefficients from each differential equation and enter them into the proper matrix. The matrix A contains all of the coefficients of the state variables in the state equation. Matrix B contains all of the coefficients of the input. Matrix C contains all of the coefficients of the state variables in the output equation. And the matrix D is null since we do not have any direct feedback. Now that we have translated all of our differential equations into standard form with matrices, we have correctly modeled our circuit with state-space representation. For more information on how state-space representation is derived, please read our paper.